EV1 linear combinations is sort of the heart of everything that we do later in Euclidean vector section. We need to be able to think about how these different combinations of vectors, linear combinations, end up resulting in our spanning sets, how that's required for basis, how we can use that to check if they are linearly dependent or independent. So this is at the heart of everything. The very first question asked us to write a statement involving the solutions to our vector equation, which means we need to write a vector equation that makes sense for this particular context, and then we need to say something about the solutions to that vector equation. Now, if we're trying to show that some vector here is a linear combination of another set of vectors, this is telling us where our equal sign is going. We know that we want to be able to show 2, -5, 4, 2. This vector is a linear combination of the others. So we've got that lovely is word. This is probably the most straightforward of all of the vector equations we have to write in all of our EV standards. Now, we want to show this is a linear combination of those vectors, so we need each of the vectors. 1, -2, 3, 3, and 1, -1, 5, 7. And then we need a linear combination. So we're going to need some multiplier here for each of them. We have some C1, C2, and C3 that are all real numbers here, some scalar multiples of those vectors, right? Now, right now we've done this part. We have a vector equation, check. We have not finished up writing a statement about the solutions to this vector equation. If this is a linear combination, there is some way, at least one, that we can write out this linear combination. So we want to write something, a statement involving solutions. We would write has at least one. And as we discussed in class, if you are like wanting to be really, really concise and have to write a lot less here, then you just say is consistent. Those are the same thing. Now, obviously, the is consistent isn't quite as clearly answering this question, a statement involving solutions, but as long as we know consistent means it has at least one solution, we can use those things interchangeably. Anything else I was going to say here? Oh, and then it is okay if you want to come up here and label these vectors and use that in your vector equation instead of writing everything out if you want to be a little more quickly to write this. All right. So then we scroll down and the next thing says, determine if the statement you wrote is true or false, explain how you know. And we have a reduced row echelon form of this augmented matrix that represents our vector equation. Yes. So we go, sweet. Looking at this, we know, yes, our statement is true. And then we have to be kind of careful here. Like I said, folks are sort of willy-nilly saying the matrix has infinite solutions, when in reality we're talking about that system of equations or that vector equation having infinite solutions. The vector equation has infinite solutions. Look at us using, what was that, LE3? Solutions / our vector, which I haven't labeled yet, so I'm just going to pretend I have, is a linear combination of those other three vectors. Right, so something like that, making sure that we're really being clear. I don't love the use of the word it unless we've already given some sort of like noun, right, in the sentence ahead of time. So if we just say it has infinite solutions, what the heck is it? So yes, make sure that you're really clear here. One of these two statements here is, all three of these are decent, right? Our statement is true. Obviously, that's referring back to our statement in part I. The vector equation has infinite solutions. That is referring to our statement in I. And then, or you could say at least one is perfectly fine too. And then our vector is a linear combination. That brings us back to the actual question that was asked. All three of these are equivalent. And then we can decide how do we know this? So like that's the second part. We've answered part one, explaining how we know. In the augmented matrix, we have no inconsistencies. And we see a free variable slash non-pivot row, which leads us to see that infinite solutions to vector equation. Now I don't need that much writing, but I'm just saying, like, technically I would like to see both pieces. The statement using correct wording, either referring back to the vector equation, the statement that you made, or this idea of a linear combination, and then something about, well, we don't have those inconsistencies of 0 equal to 1. We can see the infinite solutions because we know we have that free variable, something, right, to give us that final answer.
Either, but
and since we do have an answer, and that answer has an infinite number of ways to write it, we then have to go ahead and write our statement. What is that linear combination? So I'm going to go ahead and just be like, I'm being lazy. Now, the simplest thing we can do here, right, if we wanted to write our solution set, we know that our C1, C2, and C3 from way up above, we could rewrite that solution set as we have a free variable A for the third variable, that's C3, because that third vector is actually dependent on the first two. And then we have a 1 minus 2A and a 1 plus A. So this is the, like, if we wanted to write the solution set. Now, it's not asking us for all the different ways that we could write this, but this could help you if you want to when it comes time to actually be like, okay, well, which one do I want to use? We've talked a lot about setting that free variable to 0, so set that to 0, and then our solution that we're going to look at, a particular solution, is 1, 1, 0, which means that this vector here should be 1 of the first vector plus 1 of the second vector. That's a -1. And we can look at this and just double check. Sure enough, everything works. That is completely true based on vector addition. And we have our final answer. Now, that is not the only way that you could have written this, of course. You could have set A equal to anything and found a different linear combination. So if you wanted to just show off here, alternatively, let's just set that to 1. So we'd have this equal to 2 of this first vector. That's 1 would be minus 1 of the second vector. And then plus 1 of our last vector, which is 1, -1, 5, 7. So like I said, infinite number of different answers here that would have been correct. There's also an infinite number of incorrect answers, but this is all it wants, is a linear combination. So just one that fits this bill and gives us back out that vector we were interested in.